All right, I'm back. So the last type of energy that we're going to focus on is this idea of thermal energy. Okay, and this is going to come into play when I have situations where I have a force of friction. So we know that when two things slide past each other, as they would if I have a force of friction and there's friction between the two surfaces, then some of our energy is going to be transferred through that interaction. The two materials will heat up, so I will have this transfer of thermal energy between the two surfaces. So thermal energy itself does not get an equation. It is similar to how in forces, the force of tension did not get its own equation. Okay, we're going to find thermal energy through something called a conservation of energy equation, just like we would have found the force of tension from the summing of our forces. And so maybe thermal energy, this interaction will make a little bit more sense when we get down to an actual example using thermal energy. But anytime there's the force of friction, we run into this idea where we have a transfer of some of our energy to thermal energy instead of what I'm going to call a usable energy. So any of our usable energies are ones that can cause motion or are motion, okay? And that's the same idea as something called mechanical energy. So you may see mechanical energy referenced sometimes, and mechanical energy is referring to potential energy or kinetic. It's the energy that can cause the potential for motion, or it's the energy of the motion. Those are mechanical. Okay. Thermal energy is going to be separate. It's not really usable. It's not going to cause motion. It's going to actually end up taking away from our motion. Okay. But the first example we're going to work with here is our popper toy. So the one that I showed you in the beginning of the last video. So our popper toy here. Okay, so I want to look at the popper toy in 3 different spots of its motion. Okay, so I want to look at it when it's down here and it is on the ground with the spring. I'm going to call it a spring instead of the mesh. Okay, but an elastic, something that is compressed. Let me get rid of that little dot that I just drew. Okay, so I'm going to call this position 1, okay? And then I want to look at it when it is mid-air, okay? So it's somewhere up here. It has not reached its max height where it would stop, okay? So it's just moving through the air upward. We'll call that spot 2, okay? And then I also want to look at it up here at its max height. So when it reaches the max height, that's the point where it's going to stop moving and it's going to turn around and come back down towards the ground. So at our top height here, we are not moving, okay? So I'm going to call this like the bottom of the ball, I guess because I'm drawing it as a ball, I'm calling it a ball, of the popper toy, okay? I'm going to call this the point where y is equal to 0. That's our reference spot. That's when the spring is compressed, but it's about to be let go, and I'm going to call that y is equal to 0. So then when I come back over here, and I'm at the bottom of the toy, but it's somewhere up in the air, I'm going to call that y1. And then lastly, when it's up at this maximum height, our point up here at the bottom, which would be our max height, which I'm going to kind of miss the bottom a little bit. Sorry, it won't let me get it quite at the bottom. I'm going to call that y2. Okay. So when it's at y is equal to 0, it is not off the ground, okay? But my mesh thing, my spring at the bottom, it is compressed. So when that spring is compressed, I have that spring energy, okay? So then if I look at 2, at spot 2, it's moving up from the ground, so it's moving, okay? So it would have EK. But it is also at a position of y1, meaning that it is above the ground. So it has the potential to fall back to the ground because it is above the ground. So it has EG, but EK, but it also has EG, and I'm going to call that EG1 because it's the EG when I'm at Y1. And then at spot 3, it has stopped moving, and it's about to move back down towards the ground, but at this moment it is not moving, so it does not have EK, but it is above the ground, so it's going to have EG. So I'm going to call this EG2. Okay, and because energy is conserved, okay, that's going to tell me that I should have the same amount of energy here as I have here, as I have here. All of those energies should be equal. So that means this elastic spring energy should be equal to this EK plus EG, should be equal to this EG up here at the top because energy is conserved. Okay. And so to solve for any of the different things, like I want to solve for this gravitational potential or this kinetic or this energy from the spring, I need to write something that's called a conservation of energy equation. Okay. And I have a little tool that's going to help us do that. So this tool, I call it an LOL graph, and maybe in just a moment you will see why. Because I'm going to do a little L, which is technically a bar chart, a circle, and then a second L, which is going to end up being a second bar chart. Okay, and so it looks like LOL, hence calling it an LOL graph. Okay, the first L is going to be where I'm going to represent the energy I have in the beginning in terms of bars. The second bar chart is going to be where I'm going to represent the energy I have at the end in terms of bars. And then the O in the middle is there to help us keep track of what objects we're looking at, okay? So when we're talking about energy, and when we get into the idea of work, which is our next thing we're going to look at next at the end of this week, we're going to talk about work. The big idea here is what is in my system. System being a combination of objects, okay? So this part in the middle will be expanded upon when we get to work, but for now, I want to think about everything that could apply a force in this scenario, okay? So I have this spring. Sorry, my mouse just got weird. Okay, I have this spring. The spring applies a force. I have the earth, right? Because the earth is going to apply a force of gravity on the toy as it moves up. Okay, and then I have the toy itself because we have our Newton's second law. If the spring applies a force on the toy, then the toy applies a force on the spring. And if the earth applies a force on the toy, then the toy applies a force on the earth. Okay, so here in the middle, I'm going to write the words toy, earth, and spring. Okay, so this is me defining my system. It's saying what objects I'm looking at within my system because energy is conserved within a system. Okay, so it's important to know what your system is, right? So I'm looking at anything that can apply a force, writing what it is in the middle to define my system. Okay, so then for this first LOL graph, we're going to end up drawing two. But for the first one, I'm going to start from position 1 and go to position 2. So position 1 is over here where we have our spring potential energy or our elastic potential energy. Okay. And then spot 2 is this one halfway up where I have my kinetic energy and I have some sort of gravitational potential energy because I'm at position Y1. So I'm going to represent these energies by bars, okay? Now, the amount of bars I use is arbitrary, but the bars on one of the L's has to match the amount of bars on the second L. So I'm going to split this up into 3. So I have 1, 2, 3 chunks, and I'm going to use that to represent my elastic potential energy in the beginning. And then at the end, I have kinetic and I have gravitational at this position 2. I don't know which one's greater. I don't know. I could have more kinetic. I could have more gravitational. They could be equal. I'm not sure. I don't know enough information. Okay. So again, this next part is arbitrary. I'm going to say that I have 2 bars of EK and 1 bar of EG1, okay? But the only thing that matters is that I have 3 over here, 1, 2, 3, and I have 3 over here, 1, 2, 3. And that's going to represent that my energy was conserved, that I have the same amount over here as I do over there. I tend to do it in chunks of 3, but again, that's completely arbitrary. You could have made this 2, and then this 1, and this 1. You could have made this 4, 2, and 2, 5, 3, and 2. It does not matter at all. So this is just a tool to get our thoughts together, okay? But the next step is that I want to set this bar, this first bar, equal to the second bar, or the second bar chart. So I'm going to set the left equal to the right. So I'm going to say that our spring potential energy is equal to our kinetic plus our EG1, and that's going to be our conservation of energy equation, which is going to help us solve for stuff. So I know that the spring potential energy or elastic potential energy is 1/2 kx squared. I know that kinetic is 1/2 mv squared, and I know that gravitational here would be mgy1. Okay, so then this would give me the equation with the ability to solve for k or x or m or v or y, depending upon what the question is asking for. Okay, now I could do the same thing if I wanted to go from position 2 to position 3. Okay, so I could make this first bar position 2, this second bar position 3. I could go from position 1 to position 3. So I can make this first bar 1, the second bar 3. Okay, so this same process can be followed for any combination of those 3 different positions, because energy should be conserved within this system. So the energy should be equal at all of those different spots. Okay. So next example I'm going to do is one where we're going to bring some of this idea of thermal energy into play here. So I'm going to do the example of a baseball player sliding into home base. Okay. We had a question on, I don't like how lopsided that was. Oh. Okay, take 3. Okay, better. We're just going to leave it like that. We had a question in one of our forces example sets where you had a baseball player sliding on the ground into a base. Okay, and so if I were to draw a free body diagram for that baseball player, he was moving when he hit the ground. Okay, so let's say he was moving in this direction. I'm going to say that right is positive, so he's some positive velocity to the right. So he's moving, but then when he hits the ground and he's sliding, the only force acting on him in this x direction is the force of friction. So because I had that force of friction and that was my only force, then the baseball player would end up sliding to a stop, right? Okay, so I went from having a velocity sliding to a stop, and if I'm stopped, then I have a velocity of 0. Okay, so I went from having kinetic energy, right, to having no kinetic energy when he was stopped, right? So we can draw another little free body diagram, I guess, here and say this is where our velocity is equal to 0. This is where he stopped. So here he would have EK, okay? But here he has no EK, but that EK can't just disappear, okay, because energy is conserved. So we go from having kinetic energy to having thermal energy that is from the interaction between the baseball player and the ground, okay? So yet again, I'm about to run out of time, stopping the video, pick it up here with the next